So, magnetic force, the motor rule. You need to really have the last session in memory. The quick reminder is this, that a conductor in a magnetic field experiences a force. Its magnitude, the magnitude of this force is BIL, and the conductor needs to be perpendicular to the lines of flux or the field lines to experience the maximum force. And we use Fleming's left-hand rule to help us to remember this. Today, or in this lesson, we're going to really implement all this to explain how a motor works and how a motor turns. This is a GCSE little picture of a motor. The motor's using the turning effect that's produced by these two forces. Now, just to start us off, the main parts of this motor are the coil of wire. So you can see there's a coil of wire going around like this, and then back out. It's connected to something called a commutator, which we will start to look at more. But this commutator means that as the whole thing turns, the commutator will spin, and it will go connected from the positive side of the battery, and then it will spin, so it's connected to the negative side of the battery. There's a good reason for that. If we just turn it, get it to spin, there we go. We can see that there are forces on either side of the wire. Now, we are only concerned with the forces on the two parallel sides of the wire here, because these are the current here crosses the magnetic field lines. You can just about see these grey arrows. That grey arrow there crosses the magnetic field lines at right angles. If you imagine the current on this side of the coil and this side of the coil, it doesn't cross the magnetic field at right angles, so there's not going to be a force due to that, whereas these sides of the wire will cross at right angles. You can see if you did Fleming's left-hand rule, with the magnetic field going from north to south and the current here going into the screen, you would get a force downwards. And on this side of the wire, with the current going from north, the magnetic field from north to south, and the current coming out of the screen, you're going to get a force upwards. As it continues, there comes a point where the whole thing spins, and just before the current changes direction, these brushes lose contact. These brushes here lose contact with the commutator, so the current switches off. Because the thing's already spinning, its own momentum carries on turning, and then it will go a little bit further where the direction of the current now swaps. So here the current is now going in to the screen, which means there's a force downwards, and here the current is coming out of the screen, which means there's a force upwards. Now this means that the force on this side is always down and the force on this side is always up, which keeps it turning. Okay, we need to do a little in-depth analysis of this and why it turns. This is a picture of a motor, obviously far more complicated than the one you've just seen, but we're going to use the idea of couples, which is a turning effect when you've got two turning effects around a pivot that will turn. So you need to remember a little bit of your year 12 knowledge. Okay, here's our diagram. This is a two-dimensional version of what you've just seen. Here is the side-on view of a motor. To help, maybe if I draw on, this is the sides of the motor that you can't see. So you'd have the coils of wire sort of doing that, going into the board. Okay, so coil has sides of length L. These are going into the screen. So the length of this side here, this is actually what I mean in terms of length L. So that side there is length L. The width of the coil is W, so this is the width of the coil. This is what you can see. The area of the coil is L times W. If I multiply L times W, I will get the surface area of the motor or the coil that's spinning. The current in the coil is I. Note the direction in each case, and the coil has n number of turns, so there are many turns of wire going around. Yeah, this coil isn't just one piece of wire. I've shown it here by having many turns of wire on this particular coil. And B is the flux density, shown in red. So the flux density here is from north to south, so our magnetic field lines, or our lines of flux, are going across the screen. The long sides of the coil L, they cross the magnetic field at right angles, so each of them experience a force F. Now the magnitude of this force we know from last session is BIL. but instead of a length L, if we've got n number of turns, that will cause n lots of L. So our total force on each of the long sides of the wire will be BIL multiplied by n. Now, because the coil is pivoted and there are two equal forces opposite direction, this is the force up and this is the force down. So because they're pivoted in the middle, you get what's called a couple. Now, the magnitude of a couple is the magnitude of just one of the forces multiplied by the perpendicular distance between them. So here we've got the magnitude of this force, which is BILN, multiplied by the perpendicular distance between the forces. In our case here, it's W. So if we just carry on, so here we go. The torque produced is BIL multiplied by N, so that's the total force. We've got to times that by the distance between them, which in our case is W. Just to simplify this, it's BILWN. You can see that the area of the coil is LW. So this quantity here of LW, we can say LW is A. So basically we can say that the formula is BIAN. Okay, what's going to happen now as the coil begins to turn? Will the torque change direction and will the torque change in magnitude? Okay, let's have a look. This is the same idea, all the same quantities, but now our motor has turned. Notice that the force is still upwards and downwards on this side, but we have now got a different perpendicular distance between the two sides. It's no longer W. The perpendicular distance between the two forces is now D. Okay, so at an angle, I've just called this alpha. This angle's alpha to the field lines. Using trig, the new perpendicular distance between the line of action of the force is W cos alpha. To do that, you would effectively make this into a triangle. Okay, so you'd have a triangle such as that. And this angle here is alpha. Okay, so from this triangle here, to work out what D is, D would be cos of alpha. D is W multiplied by the cos of alpha. If you do your trig triangle there, that's easy to work out. Okay, so we have now got that our total force is force times distance, which is BIL multiplied by N, and this time we're going to multiply it, instead of by W, the distance between, perpendicular between is now W cos alpha. So again, replacing the area LW by the letter A, just to remove the L and the W. Our final formula is that the total torque is equal to BIAN cos alpha. Now, we need to work out when this is a minimum and a maximum. So if we just go back to a pointer. Okay, if the angle alpha is 0, so if this thing is parallel to the field, then cos of 0 is 1. So this is when the whole, this side of the motor is parallel to the field, so it goes straight across. This gives us a value of 1 for this cos alpha. So the total torque becomes BIAN. So the total torque here is BIAN. Now that's going to be its maximum. As it turns, the value of cos alpha is going to reduce from 1 all the way down to 0, and it's going to be 0 when the motor is vertically up. So when the motor is vertically upright, then there's going to be 0 torque, because the quantity cos alpha is 0. So BIAN multiplied by 0 is all 0. So maximum torque is when it's in its horizontal position, and minimum torque is when it's in the vertical position. If you made the motors in the lesson in the lab, you would have noticed that when you start the motor spinning, it had to be horizontally across between the magnets. Okay, finally, just in case you need to see all this working, well, this is the motor working. This gives you an idea of the forces and how it changes using the commutator. You've got an end-on view, which does simplify it, where you need to have the three-dimensional view in mind to realise that, if I just pause it, the forces are on the sides of the wire that are into the screen.